These are the previous year questions, and these are also very, very important. That question they used to ask always. Maybe numbers will different. Okay. So first question is what here? Convert binary to octal. So here in this case, whenever number is given, so here suppose fortunately all numbers are before decimal, after that decimal is not there. So from decimal we'll make the grouping left side, and from the decimal right side. So octal means base is 8, so 2 to the power 3 is equal to 8. So we'll do the grouping of 3 bits from the decimal left side. Okay, if right side also will be there, so decimal right side, your decimal is here, so left side, so we'll make the group of 3 bits. So first one is what we have, 110. 110 is equivalent to how much? 6. Next we have 101. So 101 is what? 5. And again 101 is what? 5. So finally this will be 655 in octal numbers. If suppose for example someone feel difficult, then what we'll do? You have to convert binary number into decimal. Okay. So again, if some question is there, we'll discuss about that. And from decimal, if you divide by 8, then it will convert into octal. And again, you have to arrange the remainders. Okay. Next is the define universal gates. So universal gates are NAND and NOR gates are called as the universal gates. Okay. Why it is called as the universal gates means all other gates we can design with the help of NAND and NOR gates, and these gates are economical also. Next question is convert the binary number to corresponding gray code. So to convert the binary into gray, what is the logic between this? We are going to use here XOR gate truth table. So first number we'll write as it is. Okay. Next we have to take the XOR of first two numbers, first two digits, first two bits. Okay. So 1 XOR 1, what we'll get here? 0. Again 1 XOR 0. 1 XOR 0 is what here? Again we have here 1. Again 0 XOR 1, what we'll get here? 1. 1 XOR 0, 1. 0 XOR 1, 1. 1 XOR 0, 1. So in case of XOR gate, if only one input is high, then output is also high, otherwise output is 0. So this is the equivalent binary into gray. Okay, this was the binary numbers and this is the gray. So in the exam maybe bits will be different, but process will remain same. Next we have draw the logic symbol for 2 input XOR gate and write its truth table. So for the XOR gate, you know that XOR gate expression we are writing A XOR B. Okay, or this is also written as A B dash plus A dash B. So symbol of the XOR gate is like this. So here we have two inputs. One input is A, another is B, and output is what here? Y. So to write the truth table of XOR gates, so we have inputs and again we have corresponding output here. So you have to make the tabulation like this. Here we have two inputs, A and B, and we have output as Y. So now finally here, with the help of 2 bits, what are the combination? 0, 0, 0, 1, 1, 0, 1, 1. So first 2 bits are same, so output is 0. 0, 1, only one bit is 1, so 1. 1, 0, again, only one bit is 1, so 1. Last one, 1, 1, so output will be 0. Okay, this is the truth table of the XOR gate. So here you have to write truth table, then it will have better representation. So like this, suppose they have asked here XOR gates. So like they will ask the another gates also. So truth table of all other gates also you need to prepare. Next, this is the long question, very important questions. Okay, again here, this can be asked in a different way. But what students are doing mistake here, that is very important. Here what is given? 8-bit data word. So this data word is here. This is our message. Okay, these are the message bits. So students get confused. Sometimes they're thinking this is only received bit or this is only transmitted bit. Like this they're thinking. Okay. So data bit means these are the our message bits. So how many data bits are there? 8 data bits are there. Okay. So now what they're asking, generate 12-bit even parity composite word for the Hamming code that corrects and detect the single error. So here only we need to generate. They are not asking that you do the detection also, correction also, but how we are going to correct, how we are going to detect, that we need to explain. So 8 are the message bits and they are asking here we should have how many bits? 12 bits. So that means 4 will be the which bit? What we call parity bits. Okay. Otherwise, in general, suppose here is not given 12 bit means we have to find the number of the parity bits. For that, what is the logic? To the power p minus 1 should be greater and equal to p plus m. So here m is given how much? 8. Now suppose we'll take p as the 4. So to the power 4 is what? 16. 16 minus 1 is what here? 15. So it is greater than 12. Okay. So that's why message parity bits required is what here? 4. So now you know in this case that when parity bits are 4, so that position of the parity bits again we have to find. So the it is the total how many are there? 4. So that you will write 4 means in the binary you know that count will start from 0, 1, 2, 3. Okay. So first you can write here parity bit position. That is important and proper representation is also important in the exam. Don't be in hurry and worry. So first parity bit position, what will be there? You know that it is the binary. So to the power 0 is what? 1. So what we'll write here? P1. Again to the power 1 is 2. So that is P2. Again to the power 2 is 4. So that will be the 4. To the power 3 is 8. So that is the P8. So these are the position of the parity bits. Next, we have to decide what will be the value of the parity bits, right? So if you want to see here, we can write, we have 12 bits are there. So that bits position we can write. So generally standard books, they're writing from the left to right. So here also we'll follow the same thing, left to right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. These are the position. Now here, what will have? Position of the parity bits are what here? It is here P1. This is here P2. Next is here P4. Next is the P8. Remaining are the position of the message bits. So message bits also we are counting from the left to right. So first bit is 1. Next is we can use the different representation. So first one is what here? 1. This is again 0. Again we have 1, 1, 1, 0, 0, 1. This one we are writing from here, the given message bits. Okay. So here you can write the message bits equal to this. After that, this is the representation. Now very important is that what is the value of the parity bits. So for the value of parity bits, here what is given? We have to use the even parity. So even parity means number of ones should be even. That we are going to see. If it is not even, we'll add 1, then it will become the even. Okay. So for the value of parity bit P1, we have to look the position. Those position, what are the position? If you're able to remember from the previous one. So for this, you can use the XOR gate. Otherwise, directly you can use the sum also. On the basis of that, you can say. So in the XOR of what are the position? First one itself is the parity bits position, so that will leave. So 1 gap. So 1, next 2 is gap 3. Next gap is the 4. So next is the 5. Next is the gap 6. Next will be 7. 8 is the gap. So 9. 10 is the gap. So 11. 12 will be the gap. 13 will be next. So 13 is not there. So finally, these are the position you have to check. Okay. So third bit is what here? Third is 1. Okay. And fifth bit is what? 0. Sixth bit is we should not take. Seventh is what? 1. Next is the ninth bit. Next is the 11th. So now here you see that number of ones are odd. Okay. So here you know that XOR function is going to represent the odd function. So here its output is going to be 1. Otherwise, just to think that number of ones are odd. So if you add one more one, it will become even. Otherwise, just keep the logic of the XOR gate. Similarly, for next what we have P2. So for the P2 again XOR. So start with 2. So 2 is already position. So 3, 2, 3, gap 4, 5. Next we have 6, 7, gaps 8, 9. So next what we'll have 10 and 11. So like this, if you check, so here also we'll get 1. Similarly, P4. So P4 again XOR. So it will start where 4, 5, 6, 7, 8, 9, 10, 11 is gap. 4 consecutive, 4, 5, 6, 7. Again 4 gap. So last will be what? 12. So here again you have to see that bit combination. You are going to get here again 1. Last one is what? 8. So again XOR of this. So now 8 consecutive we can take here. So 8 is already P8. So 9, 10, 11, 12. So up to 12 only we have. So again, if you see the combination of this one, so here already number of ones are even. So that here P8 value will be 0. So that we can write here. So finally, the transmitted signal, what we are going to transmit here, so that bit position will be like this. Okay. So here we can write separately. So this video may be a little bit lengthy, but it will complete all concept it will give for the related to first units. Okay. So P1 will be what here? 1. P2 is also 1. And P3 is the message bits. P4 is what? 1. P5, that is message bit, will copy as it is. P8 is 0. So again, message bit we are going to copy as it is. So these are the combination of bits which is being transmitted. So here if you try to count that number of ones should be even. 1, 2, 3, 4, 5, 6, 7, 8. So here number of ones are even. Okay. Now for the detection, in that you have to generate the error. On the basis of that you have to detect. So for the next topic, what will be the next concept is what? Detection. From the obtained message we have to detect the errors. So detection of error. So for that we are going to use the correction bits. Okay. So if suppose for example we are going to make some change in the information, and if error is going to occur, so that how we are going to recognize that one. Okay. So now for that for the correction, again if you see that we have logic for that one. So that is the C1. For that again we have to take the XOR of, like it is P1, 1, 3, 5, 7, 9, 11. So these are the bit position we have to check. Suppose if C1 is going to become 1, okay, then we'll have error. That means we'll see the combination of the error. So suppose for example, so here bit combination has changed like this, that C1, again here also we'll take the concept of even parity also in the receiver. So suppose C1 is 1, okay. So that means error is going to occur. If all will be 0, then no error. All means here C2, C4, C8. So again for the C2, we have to see the combination XOR of 2, 3, 6, 7, 10, 11. Now suppose I am taking this is the 0. Then what will happen here? Due to this, no error. Okay. So finally better we can have, first you can find the C1, C2, C4, C8 also. So C4 again XOR. What are the position we have to check? 4, 5, 6, 7, 4 gap, 12. So suppose this one also I am taking as a 0. C8 XOR. Again we have for this bit position 8, 9, 10, 11, 12. So now in this also we are taking 0. So in this situation, what we are seeing that C8, C4, C2, that combination is again here C1. So what is the bits? 0, 0, 1. So 0, 0, 1 is equivalent to what? 1. Decimal equivalent is what? 1. So that means first bit has error. So first bit has error means what is the first bit? It is the first parity bits. So that bit should be changed. If it is 1, it will change to 0. If it is 0, it will change to 1. In this given problem, if you try to see that transmitted and receiver, both we are taking the same bits, then all values should be 0. Just we can check one combination here. It's taking already a lot of time. So for the C1, suppose you check 1. First bit is what? 1. Third bit is 1. Fifth bit is 0. Seventh bit is 1. Ninth bit is 1. 11th bit is the 0. So here number of ones is already even. So here C1 is 0. Okay. So for this combination, what we have taken, same received bit, then C2 also will get 0. C4 also will get 0. C8 also will get 0. Then in same information we are going to receive, then finally it doesn't have any error. Okay. So if anyone is going to become 1, correction bit, anyone is going to become 1, then there is the error, and that combination will show that which bit having error. Okay. So like this, you have to take care what are the position we are going to check. Okay. So for the P1, 1 gap is there. For P2, we are pairing of 2 and 2 gaps. For P4, we are taking combination of 4 and 4 gaps. It will always start from the parity bit position itself. Okay. P8 again, we have 8 combinations and gap will be there. So like this in C1, C2, C4, that parity position is included. So this first one is the parity position. Okay. All these are the parity positions. So this is the question Hamming code always they're asking. That is the very sure question. Maybe you have different information, but you have to understand whether message bits are given or received information are given. Sometimes received information is given. That means it consists of message bit as well as parity bits. Okay. And one of the very, very important questions is here about conversion from the one number system to another number system. This is also 100% sure question that you are going to get here. Okay, this is the again due to some technical problem. Okay, so this is the again sure question here. So now this sometimes they will ask you have to find the radix or you have to find the number. So if you have to find the radix, that is little difficult. If number means it is the easy. If they're asking radix also means let's see, we'll see how we are able to find. Okay. So first question is what here you have to convert this right side is given. It is the octal and they're asking here what is the value of the x. So for that situation, what you'll do here, you have to use that concept how we'll find the one number system into another number system. if you are going to feel difficult. So finally, this octal or particular given which is given, that will try to convert into the decimal. Okay. So then easily you can do from there. So it is what here we have 141448. This is the octal number. Okay. So octal to decimal, if you have to convert, what will be the value? Or this one we want means you can convert into hexadecimal or any one. So now first we'll teach us how to convert this one in the decimal. So now this value, it is the weighted code that you know. Okay. So here what we'll write? This is 0, 1, 2 position. So what we'll have? 1 into 8 to the power 2 plus 4 into 8 to power 1 plus 4 into 8 to power 0. So finally it is what? 8 to the power 2 is 64. Here it is 32 and here plus 4. 8 to the power 0 will be 1. So finally this is going to be equal to how much? 100. Okay, this is 100 is what? Decimal. If any given number system you are going to expand in this format, you will get the decimal equivalent. So now it is the decimal. Now decimal, you check that this number it is now going to be equal to 1 to 1 x equal to 100, and this is the decimal number. So now if radix is here x, so this can be written as how? 1 into, so this is the into x to the power 2 plus 2 into, these are the coefficient, 2 into x to the power 1 plus 1 into x to the power 0 equal to how much? 100. Whatever number system is given, if you will expand like this, it will be equal to the decimal. So finally, this one, what we'll get here? X square plus 2x plus 1 equal to 0. Okay. So finally, this 100 you bring this side. So what we'll have? X square plus 2x minus 99 equal to 0. So this 99 you have to factorize. So this is the quadratic equation. I'm not going in much detail now. So this will be, factor will be here 11x minus 9x minus 99 equal to 0. So here this is the concept of p plus q. This p plus 2 is 1, q is 2, and p into q is what here? Minus 99. So this one we have to factorize like this. So this one is here 11, this is the minus 9, and finally 11 minus 9 is going to give us 2. Okay, so that's why we got here. Now common is x, so x plus 11 minus 9, again x plus 11 will get here 0. So finally this is x plus 11 into x minus 9 equal to 0. So from here x equal to 9 and x equal to minus 11. So negative number will not be radix, right? So x equal to 9. So that means this value x is what here? 9. So this is equivalent to 121. Radix is the 9. Okay, this is the standard way to find the unknown radix. This quadratic you have to go through this. Another question if you have, second one is what? Here given A to C. It is 16 means hexadecimal, and you have to find in the octal. So this is the quite easy when we have to convert hexadecimal, octal, all these things. So hexadecimal means this hexadecimal A is means equivalent to how much? How much equivalent? 10. Okay. So 10, how we'll write in the binary? 1010. And 2, this is also write with the help of 4 bits. So 0010. C is equivalent to what? 12. A is 10, B is 11, C is the 12. So 12, how will write? 1100. So D, E, F is the 15. That you have to keep in mind. Okay. So this is in the now hexadecimal, and we have to find the value in the octal. So again here logic is that we have to make the combination of 3 bits. We are converting to octal. So from decimal left, from decimal right. So decimal is here last. So again this 3, again this 3, and this 3. So finally this will be 101 is what? 5. 000 is 0. 101 again 5. And 100 is what? 4. So this is equal to 5054 in the octal. Similarly, third one, 128. It is given in the decimal. Again, now you have to find radix. So whenever radix they are asking, so similar process you have to use. Okay. So you have to convert this one in the, it is already in decimal here, so no problem. So just you have to expand this one. So here you'll get the quadratic cubic equation. Okay. 4 terms are here. So you'll get the cubic equation. Okay. So here you will get x equal to 5. Otherwise, just I'm telling like in easy language. Now, if it is decimal number, so by which number you will divide 128? So that first remainder will be 3. Like that also you can check hit and trial method. But this method is the best way to find. So now here if you divide 128 by 5, so you will get 2 times 10, 5 times 5 is 25, so 3 will be remainder. Since this is the remainder, first remainder, this is second, am I right? Third, fourth, like this. So you can try by this method also. So your radix will be 5. You try this. Next we have 1, 2, 4. 1, 2, 3, 4. Okay. This is given in the base is 6 here, see, and we have to find the decimal. So if any number, just you have to expand. This one you'll get in the decimal. So what we'll write here? This can be written as 1 will be the coefficient 6 to the power 3 plus, how we are writing 3? 0, 1, 2, 3. Weighted code. Again we have 2. Again 6, radix is 6. 6 to the power 2 plus 3 into 6 to the power 1 plus 4 into 6 to the power 0. If any coefficient is 0, that also if you are not writing means that's not a problem here. So finally in this case, if you simplify this, you are going to get here 310. So this x value will be here 310. So one more we have here, fifth one. Okay, so that fifth is what it is easy. Binary is given. We have to convert into hexadecimal. So for the binary numbers, if you have to convert into hexadecimal, what is the logic? Can you remind? So hexa means to the power 4 is 16. So here we'll take combination of 4 bits. Okay. So from decimal left side. Here we have 3 bits only. You want means you can add 0. Okay. So this equivalent to how much? 0, 1, 1, 0 is what? 6. Okay. And this one 1, 0, 1, 1 is how much? 8 plus 3 is what? 11. And this is the 11. And finally, this one asking us in what, which basis? Say hexadecimal. So 11 we are not going to write in the hexadecimal. So this 11 will write as the B. A is 10. Okay. So finally this will become how much? 6B. Base will be 16. Radix will be 16. Okay. So like this is very, very important question. Always they used to ask. Directly, indirectly, different number will be there, but they are going to ask you this question always. Okay. So next we have another is to convert. This is the concept of the sum of product and product of sum. Okay. This type of the question, sometimes maybe they will ask you NAND NOR implementation. That is also possible. Okay. So that one, how we are going to do, that we are going to see. So here we are going to use the concept of the De Morgan's theorem as well as complement. So here what is given? F equal to A plus B dash C. So here you are seeing that 3 variables are there. A, B, C are the 3 variables. So first if you look for the sum of product. First we'll go for the SOP. SOP is what? Sum of product. So this one we have to convert into sum of product. So the first term is A. What is missing here? B and C both are missing. So here this one first we can do a step by steps. So here we can multiply this one with B plus B dash. Okay. And again in the second term which is missing? A is missing. So here this will be multiplied by A plus A dash. Why we are multiplying this A plus A dash means by using the complements, you know that X plus X dash will be equal to 1. Okay. So this concept we are using. So here again what we'll have? AB plus AB dash. That distributive law, cumulative law, all you know about this. And this one is the AB dash C plus A dash B dash C. So here in the third and fourth, we have all literals, but for the first and second terms, all literals are not there. So this will be multiplied again here. So we have AB dash. This will be multiplied by C plus C dash. C plus C dash is what? 1. So that's why we can multiply. So finally, now here we'll get ABC plus ABC dash plus AB dash C plus AB dash C. Now, if some term is repeating, no, that term will write only one time. Okay. So finally, like this, we'll have 6 terms. Whether any repetition is there, any term is being repeated, no. So finally, this is the sum of product. Okay. Similarly, we can go for the POS, product of sum. So here F is A plus B dash C. This one we have to convert into product of sum. So now this one here we are going to use that properties. Okay. So this A plus B dash C can be written as A plus B dash into A plus C. Okay. So these are the Boolean algebras rules were seen there. So now here in the first one, which literal is missing? C. Second one, B is missing. So here in this, we can add C into C dash. Since C into C dash is what? 0. And here A plus C plus B into B dash. Why we are doing this? Since X into X dash is what? 0. And this one you are using the here distributive properties. Okay. So finally, this will be written as again, same how we have written this one in this format, same thing we are going to use here also. So we'll have A plus B dash plus C. Okay. Again with second term, A plus B dash plus C dash. Similar concept here also in the second term also. So there we'll get A plus C plus B into A plus C plus B dash. This is the very important concept that we are going to use here. And finally, we got as the sum of product and product of sum. Okay. Thank you. These are the very important questions. Maybe we'll have different values, but these questions are going to come. So watch again and again and share, like, subscribe. Thank you. Thank you.